Good morning, ladies and gentlemen, and welcome again to the course on managed aquifer recharge systems and water harvesting techniques promoted by the University of Saxony. In the fourth lecture, we'll talk about water harvesting techniques, some examples from ancient mechanisms to modern facilities in Mediterranean countries and also in South America, recommendations for water reuse, design and construction criteria, exercises and additional material. Water harvesting, according to Fraser definition, is the collection and the storage process for later uses in an area treated to retain and canalize runoff water. Some common features are: it is applied in arid and semi-arid zones, where runoff has an intermittent character. Water is collected from a local origin, runoff is stored in the soil profile and in the faults of the bedrock, and in general they are applied in a small scale, regarding the area, the stored volume, and the invested capital. The classification of the water harvesting techniques is done according to the source, either rainwater harvesting for urban areas or flood water harvesting for streams and rivers. According to the storage system, it is stored in ponds, tanks, cisterns, etc. According to the use, it can be done for water supply, for crops production, and for the combination of both. And according to the vegetation production systems, we can distinguish microbasin systems with a scarce slope and external water catchments for high slopes. So, the water harvesting systems are integrated into well-differentiated zones: the catchment area, also called impluvio or collector, where runoff water is concentrated and retained, and the harvesting area, where water is stored either in the soil profile, what is called runoff farming, in specific deposits, such as aljibes or any store device, or in folds of the terrain. Also, in this dense slide, water harvesting techniques are used for vegetal production and can be grouped in three different categories. The first, microcatchments, when the rainwater harvesting system has a short circuit of water from 1 to 30 meters and runoff is stored in the soil profile. The relation between the rain area and the catchment area is from 1:1 to 3:1, and some examples are ditches, rounded furrows, contour bands, ammunas, etc. The external catchment systems is for high slope areas. Water must be stopped and stored in the soil profile. The catchment area is from 30 to 200 meters long. The relation is between 2:1 to 10:1, and some examples are trapezoidal furrows and stones masonry walls. The third category, always according to Critchley and Seeger, is the flood water farming. It is for intermittent rivers or streams in which water is collected from diversions. Runoff is stored also in the soil profile, and the relation between the rain area and the catchment is above 10:1. In the first category, water harvesting is done using existing slopes with small retaining structures, such as parallel ditches and or damming barriers. It is a water harvesting technique very usual in river basin headings. The most usual are the contour bands or parallel ditches to retain runoff and cause the enhanced infiltration towards the soil, the regolith, and the faults in the underlying rock massif. I remind these systems are for scarce slopes. In these systems, water harvesting requires a deep knowledge of the tectonics and connections between faults in the area. Also within the first category is usual deforestation or reforestation to increase the water availability and supply security. And by last, in the first category, are included the high-altitude ponds. They are used for water infiltration, re-wetting agricultural lands, and thus water reservoirs for irrigation. In the second category, for external water catchments and high slopes, water harvesting takes advantage of the existing slopes, and it is not necessary neither to intervene on the terrain nor digging furrows or ditches, as in the previous case. And the third category, or flood water harvesting, includes infiltration ponds, canals, terraces, etc. Into this category it is important to outline the amunas, which is a canal designed to capture runoff water and its later infiltration into the soil and weather rocky layer or regolith, as well as into the folds of the rocky massif beneath. We'll talk about amunas canals with a certain detail later. As good ancient examples of water harvesting and managed aquifer recharge, it's good to compare the Careo canals in the south of Spain and the Amunas canals in Peru. Talking about the acequias de Careo, it is a canal dug in metamorphic rocks diverted from rivers. The diversion is made by stones and skids layer without any concrete. Here are some specific data of this example, and the most important, water is moved across the weathered area or across the interconnected faults in the rocky massif. Another example of Careo's canals is the one from Messina, where were used tracers techniques. They use the faults in the rock massif to transport the groundwater from the ridge to the spring, and there are many different elements in the construction, from channels to forts, infiltration fields, door lines, gates, and some of them with the employ of hydraulic masonry. The equivalent Peruvian amunas is an ancestral Mar-Andine technology that conforms a hydrogeological and socio-cultural complex system. It entails strategies to manage water, lands, and crops. In contrast with the Careo canals, both pre-Columbian and from different continents, amunas systems are constructed in parallel at several altitudes in the slope of the mountain. They have a specific design to capture runoff, either from the rain or from melted snow. Amuna canals direct runoff water to recharge areas. They have extended reception surface. They were constructed seeking fractures and geological faults in the terrain, and water recovery is done by means of canals or springs, and the groundwater transit time from the recharge to the recovery area is from 6 to 7 months as an average. Some of the most important Peruvian examples are the amunas of Huarochirí, dug on volcanic rocks, forming a fractured aquifer with a certain importance due to its thickness, extension, and faulting degree. The hydrogeological behavior is represented in this scheme. From the filtration area, water flows either across the regolith or across the faults in the volcanic rocks, and water is recovered downwards from 6 to 7 months later in general. In short, they are surface MAR systems, and most of the elements present in the Careo canals are present in Amunas too. Here are some examples from a different system, San Andrés de Tupicocha in Lima district in Peru. And now we leave the water harvesting technique to talk about recommendations for water reuse, in special regarding water quality aspects. For example, in the MAR facilities is important a pretreatment of water for MAR in the origin, from wastewater treatment plants, membranes, mud lines, filters, packets, etc. It is also important to reduce as much as possible the total dissolved oxygen in the heading of the MAR facilities by means of different techniques, but the most important, avoiding the cascading and the sinking of the water to be recharged. There are also some techniques to improve the water quality during its transport or in itinerary. For example, intercalating filters, controlling the pH by means of mudstone gravel filters, etc. Once again, I persist it's very important to avoid the aeration of MAR water by means of communication vessels, open or buried structures, controlling the flowing velocity, etc. In short, it is very important to avoid the entrance of oxygen into the system. Regarding MAR design and construction criteria, some examples have been extracted for the references, such as the reservoir dams and simple dams. Their main purposes are restraining the surface runoff and facilitating the infiltration upstream the dam. These dams or dikes are constructed in ephemeral or seasonal gullies or streams. They have a permeable river bed and usually have a spillway to avoid overflowing. Drill dams is a specific type of dam with a punching drill across the dike with a double function, the energy dissipation and the direct collection of water. Another technique worth to be mentioned is the riverbed scarification, consisting of scarifying the bottom of the river so as to increase the infiltration rate across the alluvial formations. The permeable dams, check dams, and gabions are typical of semi-arid and arid regions and are built with loose materials, either cemented or retained by means of fences. Infiltration ditches are dug in the soil with a linear morphology and semicircular sections. They usually follow the contour bands and increase the infiltration and reduce the soil erosion. The distance between the ditches must be calculated by this formula and will be applied in the exercises proposed at the end of the lecture. And here is the proposal of two exercises. The first for contour band design. All the necessary data are provided regarding the precipitation, the runoff coefficient, the infiltration rate, and the students will have to calculate the distance between the different ditches. In the second exercise, a student will propose measures to get a maximum effectiveness and to avoid clogging in two different scenarios, for a wastewater treatment plant related to a SATMAR and for a battery of wells and boreholes. This exercise requires the knowledge of the 4 lectures in the course. As additional materials, some deliverables from European projects are recommended, in special from Dynamar and Marsol, which talk about more design and construction criteria. I remind this presentation is in an extended version in the MEIA project website. Thank you for your kind attention.